Okay. Hi everyone. Let's get back to the analytic as metrics. Let me just start with a short recap that we are talking about scattering. We focus on the 2-to-2 scattering, and this is characterized, for simplicity, we can consider scattering of identical scalar particles. And this is characterized by this function, which is a connected scattering amplitude, which is a function of two variables. You can think of one as energy, another as angle. And as we already discussed for a couple of lectures, even though in a physical experiment both of these parameters are real, there is a good reason to really think of them as being complex. So the fundamental object in S matrix theory, the simplest object, is a function of two complex variables. And moreover, one important point which we discussed and which will be the topic of today's lecture is that as soon as we have a function of two complex variables, you can ask what is its analyticity domain, where it's an analytic function, and so we want to understand its analytic properties. And this is the subject of our today's talk is analyticity. Now, first of all, a couple of general comments. It would make sense probably we were discussing last lecture unitarity properties of this object. We did decompose it in partial waves and we wrote some expression of unitarity. But it would be good maybe to write some explicit example of this function. Well, we will never do that in these lectures for the reason that in space-time dimensions larger than 2, no explicit example of this function is known. Because it describes interacting quantum field theory, and it is not known explicitly. It's too complicated of an object. Even though we believe it exists for pions, exists for protons, for gravitons, but I will not write it. That's the first thing. Second is that, let's say you, you perform a computation, and then your power of compute might depend on the computer you have, the table of integrals, the version of Mathematica that is installed at your laptop. So the latest version should be more powerful. So in S matrix, as you will see today, the more analyticity you have, the more power you have. So that's kind of something simple thing to keep in mind. The larger analyticity domain, the more things we will be able to say. So that's why it's a big deal. And the subject of analyticity, so of this function, if you ask me, do we know what is the maximal domain of analyticity of even these two functions? Even though this has been the subject since the birth of the theory, since the birth of particle physics, we don't know the answer to this question. So, what happened in the past is that there are several lines of attack to this question. And these lines of attack are relevant still until today. So you might try to establish, to get an idea of what is the analyticity domain of this function in a couple of ways. So first, it's what is known as So axiomatic analyticity is a subject which was very active late in the 60s, and I guess end of 50s, where you start with the axioms of QFT, and you try, so axioms, you choose your favorite system of axioms. Usually it's a Whiteman axioms, I guess you can take Kastler axioms, whatever system of axioms you believe in, and you try to go from the axioms, which are usually formulated in terms of correlation functions, to the amplitudes. Now, this path is not a trivial one for various technical reasons, but nevertheless, people pursued it, and we will discuss what was obtained. So you start from QFT axioms. The second path, so this was a one school. There was a second path, which we can call analyticity from unitarity. And here the idea is you would like, as remember last lecture we were writing formulas, discontinuity of the amplitude was equal to amplitude square. And so this was an example of non-analyticity dictated by unitarity. But in fact, the idea is much more general. You can try to use unitarity to learn about analytic properties of this object. And the key tool here to do this is what is known as Glendale Equations. And this is a program which was actively pursued by several groups in the 60s. For example, there is this famous book, Analytic Matrix, by the Cambridge group, which essentially is focused, or the core of this book is this approach. And the only thing you have to know is that, so what people have done here, people studied some singularities of the Feynman graphs. I will explain why Feynman graphs are relevant to our non-perturbative studies. And they try to classify singularities and try to find all the singularities, and then they fail, because they found that if you try to study singularities, they found that there are some very complicated ones which seem to be not under control. And so this program sort of classifying singularities of scattering amplitudes got frozen. It doesn't mean that there can't be any more progress done, but in general, sometimes you hear that this matrix failed. Well, one thing is that it's failed to classify all the singularities, and indeed there are some complicated beasts. But finally, if you want to skip all these technical details, one outcome of all the studies, and it was originally proposed by the Mandelstam, was something known as the maximal analyticity. It's a conjecture of what is can be a maximal analyticity domain of this object, and it's closely related to what is known as a Mandelstam representation. Now, there is one difference here, is that when you talk about QFT axioms, well, if you believe in your QFT axioms, then this is a completely rigorous, whereas here it is something which is less rigorous. It is more of trying to guess, and my personal take is that something based on plausibility arguments. In other words, you motivate something, and then you see that there is no obvious reason to this to fail, and then if the motivation is strong enough, and I will say it later again today, what exactly do I mean by that, then let's assume this to be true. So, for example, Mandelstam representation has not been proven or disproven, so it's an open thing, and it's completely not clear if you can prove it, but definitely we can try to motivate it better and assume it and work with it. So depending on your taste, you can either try to improve something rigorous, or you can improve something plausible. So, but these are the approaches to analyticity that people have undertaken until today. And so I would like to say a few words about each of them. So for this axiomatic analyticity, there are really a lot of literature, and I sketched the argument in the notes. But if you really are not working on it, I think it's enough to say just that you assume y is maximum, LSZ reduction, and you use various tricks to establish this. One general fact, which may be worth mentioning, is that, and which is necessary for this, is that if you have a function of, if you have a complex function of one variable and you know that it's analytic in some domain, then just based on this fact you cannot extend this domain of analyticity, because every domain of analyticity can be a maximal domain. So you can have a function which is analytic in this domain, but then it has some pole at its border and you cannot continue. The situation is different for two complex variables. This is one big difference. If you have a function of two complex variables and you have certain domain of analyticity, not every domain of analyticity is a maximal domain. So sometimes you can enlarge the domains of analyticity, and this mathematicians have understood, and physicists also have done that. So this is just something to keep in mind. So there is here a step that is known as analytic completion, which is related to this fundamental fact that the amplitude depends on two variables and not one. Okay, so let me say a few words. Let me start with this axiomatic analyticity. And it starts with the following statement. Again, this is something which I try to motivate in the lecture number 1, as propagation of signals. But if you take the scattering amplitudes, and let's say we look at the S channel, so well, in fact, let me just not say that if you take S variable to be large, this is polynomially bounded. Now, if you relate it back to KFT axioms, it's related to something called temperedness of Weightman functions, but I think at this point we can just state it as a part of KFT axioms, and so this tells you that the amplitudes do not grow faster as power of the energy. For t less than 0, you remember this was a condition when we were in the S channel, t was negative. So here this is a condition for which this growth is supposed to hold. And this is one fact. So this is called polynomial boundedness. So then there was, you can ask the following question. Given S, what is the, let's say given S positive and real, so it's a physical energy. What is the analyticity domain in T? And here I will state just two results, and then it will be enough for us to do some concrete computation. So one thing which you might have heard is that the amplitude is analytic in what is known as a Lemon ellipse. So Lemon ellipse is some region in the T plane, which is contains this region T negative, but it also bulges in the complex T plane. It's an ellipse for the reasons related to the convergence of partial wave expansion. In fact, if you have partial wave expansion, there is some simple mass theorem. If it converges on some real axis, it converges in a real ellipse. But so there is some region of analyticity, but the fundamental fact that you have to know about Lemon ellipse is that if you take its size, which is the region of analyticity, as a function of energy, and you send energy to infinity, it shrinks. So this is the region of analyticity which was established by Lehmann. And when he established this, he did not use unitarity. So he did not use unitarity. He used just QFT axioms, and there was LSZ formalism, and was managed to show that amplitudes, physical amplitudes, are analytic in some domain, which has some shape, but it shrinks as energy. So then was the big development in the S-matrix bootstrap in the 60s was the following question. What happens if you take the lemon ellipse and you combine it with unitarity? And so here what you get is known as a Martin's extension, where Martin stands for André Martin, who was a physicist here in Geneva. And the point is that, there is a technical appendix on the notes which sketches how does it happen. But the basic point is that what Martin managed to show, that in fact, you can establish analyticity in the region in the T-plane, let me call it, such that the amplitude is analytic in some fixed region. So the difference between this and this is that, as S to infinity, this does not shrinks, it does not depend on S. So if you have some lemon domain, as you send S to infinity, the size becomes 0, whereas Martin's extension says that in fact it cannot shrink, it just does not depend on S. And say for scattering of identical particles, T0 will be 4n squared. Identical lightest particles in the theory. Okay, so these are the basic, these are the main results from the we will need. And now, already these results it's enough to prove this Froissart bound. And here, just to emphasize, it was really, if you have just a lemon ellipse, you cannot prove the Froissart bound on the cross of the total cross-section. And only when you extend the region of analyticity to here, and that's what I meant by the more analyticity you have, the more power you have, you manage to prove the Froissart bound. So let me now go over the rigorous proof of the Froissart bound. So, and of course, just to emphasize, I don't want to. Of course, it's understanding all these steps in details. How do you go from QFT axioms to the lemon ellipse, and how do you do the Martin's extension? It's of great value, and I think it's more people understand it, it's better. But it will take us the whole semester to discuss that. It's really a rabbit hole. If you start thinking about it, you can really get bogged into the subtleties of definitions of Whiteman functions, LSZ reduction. So, but the punchline upon which people agree, and even this some people might do not completely agree, is this. Yes. So let us derive. Yeah, let me just, for those who are interested, give me an example of one wrinkle. I was talking about this, and saying that you start from Whiteman axioms and you derive these things. And Slava Rychkov was in the audience and said, well, actually, when you do this, you use LSZ and you use temperateness of some T products. This is not part of the Whiteman axioms. It has never been established. Subtleties like that. So good luck filling these gaps. But let me derive for you now Froissart, and sometimes it's called, and it's justified Froissart-Martin bound.
So essentially, axioms are by definition not proved. No, so.
Yes, but I think the statement is that if I make a statement, this can be proven starting from QFT axioms, and the person says, well, QFT axioms are White-Martin axioms, then you can say, okay, well, actually you have used an extra thing which is not part of White. That's what I meant. Yeah. Okay, so in fact, the honest bound, as we discussed, at some point I mentioned that the amplitudes are not strictly speaking functions, they're distributions. So in fact, a really rigorous bound is on the average cross section. So you can take, and I will prove it in 4 dimensions. Take a total cross section and average it like this. So, and we will be interested in growth of the total cross section as S, which is energy goes to infinity. And remember physically what we are talking about. What is the total cross section? It's when you collide, when two objects collide, say one particle sees the other particle, total cross section is the size of the other particle. For example, if two hard poles colliding, then the size is just a cross section of the ball. But the relativistic particle, when they see each other, when they meet in the corridor, or in the pipe of LHC, they tend to see each other's size grow with energy. And so this is the maximal size of relativistic particles. This is what we are talking about. So just so that this is clear. So our task will be to put an upper bound on this size, starting from general principles. Last time we already did it, and we got a logarithmic bound. And so the goal today is just to do it rigorously. And last time I was mumbling something about the phase shift, and today we will now just do it and review on the way things that we learned last time. Okay, so the next, it will take me now a few minutes to derive this bound, but I think it's worth it, because in fact the Froissart-Martin bound is probably the most famous result of S-matrix theory, and the way I present it, it's not often presented in the books, and sometimes it can be confusing the way it's presented. At least I find it confusing, and I hope this will be
Excuse me.
clear. Please.
I'm just confused about the weighted average. Is there a reason for this choice of?
Yeah, so there is no deep reason. We can. So here yeah, why did I put this guy here, for example, right? So I don't think there is a deep reason, but this would be a nice choice. Of course, eventually, what we expect in reality, you can just multiply, differentiate, and you will get asymptotic of this. So this is a smooth function. This is just to make it rigorous. I will put a bound on this quantity, and if this quantity is a function, then you can just differentiate. But in fact, if it's a distribution, you have to be careful. So for practical purposes, you can think, okay, well, we derive a bound, then you can differentiate. If you want to be rigorous, that's a bound. So,
Thank you.
So this is probably completely irrelevant, but you're assuming that this is still quite a good distribution, right? Because your weight function is not smooth. Like you have a theta function, I guess. Like your it's compact support, but it's because you're integrating up to S.
Yeah.
It's not smooth. So if there was a delta function, then you would have some ambiguity when you cross it. Like if you take S if there is delta minus S of minus S naught, and then you integrate up to S naught, you need to decide what the delta function does. But I guess it's not important for you.
That's true. Yeah, we can. Yeah. So the truth is, what kind of distribution are S matrices? Well, yesterday we discussed the Hilbert space. Hilbert space was given in a space of L2 functions, and so as matrices or amplitudes are kernels which can be paired with L2 functions. Of course, yeah. Now, okay, so we will now improving this. We will use everything we more or less learned so far. So the starting point is that, let me remind you, probably many of you have forgotten, what do we mean by total cross-section in terms of this object that we're talking about, which is a scattering amplitude. And this is just this. So it is a definition. It's imaginary part of an amplitude evaluated at 0 angles. It's a forward scattering. And so by unitarity, it's total probability produce everything. Now, remember last lecture we discussed partial waves. And the partial waves was the expansion in terms of some sort of polynomials, which were Legendre polynomials. And here we evaluate these Legendre polynomials at 0 angles. And 0 angles is cosine theta equals to 1. And you can check that the way I define them, I'm working in the convention where the Legendre polynomials are just 1, 1. So we simply have this. So it's just the sum. Now, what is the strategy of the proof? The strategy of the proof is the following. We take, let's say we can plug this formula, of course. Here we get some integrals of the partial waves, and what we do is that we split the sum into low spins and high spins. So this is sum of the spins from 0 to infinity. The strategy of the proof is to write the sum, introduce some random spin, some random spin L. At this point, it is not fixed. Then the proof will proceed in 3 steps. First, we use unitarity to bound this guy. We will do this now. So unitarity will be used for this, non-perturbative unitarity. Second step, we use Martin's extension. We use Martin's analyticity to bound this guy by something. And finally, step 3, we extremize with respect to L. Remember, at this point, L was chosen randomly. We can choose L whatever we want. And so, after we do this, we will get a bound that this cross-section is bounded from above. Is there any questions about that? Any questions on the idea of the proof?
Santiago Agri asks, why is j plus 1 the lower bound of the second sum and not just j plus 1/2?
Could you please repeat the question?
Yeah, why is L plus 1 there instead of L plus 1/2? I think j equal plus.
So this the spin which appears here is only integer. I think if we have scattering of bosons, then only integer spins appear here, because if you try to compute the matrix element with half integer spin is 0, just because the fields are bosons. So I guess yeah, that's it. In fact, for identical particles, not only this j is integer, but it's also even. So because we consider scalar particles, there is no half integer speed. Any other question?
Maybe remember that you can just turn on your microphone if you want and speak aloud, I think.
Okay, let me do, because I presume also it might be completely not clear at this point how does it work. So let me go a little bit in some detail over the steps, step 1, 2, and 3. And then we will have a clean derivation of the Frost-Hart bound.
Maybe can I ask you one question about the steps?
Yeah.
Yesterday you gave intuitive argument which was based on impact parameter space. Is there any avatar of that we can see in this strategy?
So yeah, the improvement, in fact, the improvement over yesterday is step 2. So the picture is that always when you think about large spin in these sums, physically you should think about large impact parameters. So before yesterday we were having trouble in rigorously bounding large impact parameters, and here Martin's analyticity will do the job for us. Thank you. That's a good point. Okay, so step 1. Bounding low spins with unitarity. This is really something trivial. It's more of a reminder, if you have forgotten, that the last lecture we have derived that imaginary part is positive, and remember it was defined like this. One, so here the real part, 1 minus e to the 2I delta j. And this delta j, this phase has positive imaginary part. This was in unitarity. So this whole thing is bounded by 2, right? That's 1 plus the absolute value of this is less than 1. So at most can be minus 1. In this case, this whole thing is 2. So this whole thing is bounded by 2. Okay, and now things become really simple for low spins. We just plug this formula into the average, and we have, I will not go over the super detailed steps, they are in the notes, but let me write it. So you get 2j plus 1. 2j plus 1 is just this nj. This is the normalization factor. And here you have an integral for m squared infinity ds prime square root. Just I will do things in 4 dimensions. So d equals 4. So there is 1/2 here, and there is 1/2 here. Yeah. And this factor is clear where it's coming from, right? It's coming from here times what's in the integral. Okay, now it's obvious. You just take this. This is a positive function under the integral. The integrand is also non-negative. So you can use the bound, which is here. This precisely cancels this prefactor. Great. It's integral over s. We're averaging between 4 and square and s. So this cancels. You can take the integral, which is just gives you some linear function in s. s minus, it gives you actually s minus 4. This s minus 4 cancels this s minus 4, and you are left with the sum j from 0 to L, and you can check that this gives you, so this is less or equal, the same, as 16 pi L plus 1, L plus 2. So that's it. That's the end of step number 1. Step number 2. And you see here, so far we just use this non-perturbative unitarity bound low spin. So step number 2, high spin. Here, what we really will need is the following things. That let's take Martin's statement that the function is analytic up to some region, and in fact, he also showed that it's not only analytic, it's also polynomially bounded. So therefore, if the function is polynomially bounded, there exists n such that this integral ds prime s prime n plus 1 imaginary part t s prime, and you choose some t naught is less than infinity. So, and really the rest is algebra, so for you to keep its unitarity and just this condition where t naught does not depend on s, and let me take for simplicity, for scattering of identical particles, say for pions, it's 4n squared. And the fact that this integral exists, it's a statement that the imaginary part does not grow faster than the polynomial. So if it grows some power, we can choose a power plus 1, say, and this integral is fine. At this point, I'm just saying that this is an is a number. And the fact that this is less than infinity, it's related to Martin's extension for analyticity. And now the idea is simply that you take the partial wave expansion and you plug it into this formula. So let's start with this an, and we plug the partial wave expansion there. So let me write it.
Excuse me, Sasha. So this Martin proof states that the function has no poles even at infinity. This is the crucial thing.
It says for fixed s, it's analytic up to some t naught, t0, and this allows you to use this expansion. So otherwise it will not. The fact that this expansion converges is related to analyticity. This is important to emphasize, yes. That you can show, and this there is a footnote in my notes that shows that if you have a function analytic in a certain domain, you can expand the Legendre polynomials in some ellipse related to this domain. And so we use this fact. And second fact that we're using is that for fixed t naught in this domain, the function is polynomially bounded. So I don't know what happens at infinity, but the statement of polynomial boundedness is simply that this integral converges. So yeah, I don't care what this number is, as long as it's. Now we do the following thing. First, a lot of somehow interesting things are related in the subject to the properties of Legendre polynomials. And some of you might have heard the last year there was a lot of activity which was related partially to some miraculous properties of Legendre polynomials, something known as the ftihedron. So the fact that you have Legendre polynomials, in fact, you might try to milk them and try to learn to get some mileage from their properties. What we are doing now is very gentle, but I will tell you some simple fact. If you didn't know, if you take a Legendre polynomial as a function of z, first of all, it's positive for z larger than 1, z larger than or equal than 1. So if you plot, take a Mathematica, plot them, you'll find that they're positive, and you will find that they're non-decreasing. So they're, in fact, for large g's, they're monotonically increasing functions. So the larger is the argument, the smaller is the larger is the argument, the larger is the polynomial. Okay, this is a simple fact which is good to know and good to remember. So now I would like to go from this equality, I would like to write an inequality. And so just follow the steps and tell me if you agree. First of all, I say that because everything here is non-negative, if I make this integral not to infinity but to some s, I will get something less. So I have this. This is a simple step. Now, second thing which you can do is that you see that again, if I want, I can bound this guy from above. If I take this factor, s prime to the some n plus 1, this is a positive power. And it only gets bigger as we integrate to larger values. So again, I can bound this expression from above by pulling this s on the upper limit. So I can write like this. You see, because I took the integrand and I took its maximal value, so therefore, and it's in the denominator, therefore it can only make the thing less. So that's one step. In fact, you can do a second step, which is, so we already have the integral over s, but we can also do the following thing, is that, remember I told you, which is the same trick but in the opposite direction. S prime goes from 4m squared to s. When s prime is close to 4m squared, slightly above, the argument is very big, so this thing is very big because I told you they are monotonic functions. Therefore, again, if I'm bounding from above, I can take, when s prime is equal to s, which is the upper limit, then this thing is the smallest, again, by the same argument. Therefore, by bounding from above, I can pull this thing from the integral. And finally, because again, everything is positive and I'm bounding from above, I can sum instead of from 0, I can sum from, say, L plus 1. And therefore, if I pull this thing away by evaluating this from S, we get here Pj 1 plus 4m squared S minus 4m squared. And here, this is gone. So, okay, I hope it was clear that so far I've been using, again, I started with analyticity, I used unitarity, and I used a little bit more, which was the properties of Legendre polynomials. So now you see that what appears here, it's exactly the contribution of high spin in the total cross section. It's exactly what we had, just sum over imaginary part from L plus 1 to infinity. So and we have average, we can also, playing the same simple algebraic trick, pull there some square root. In fact, we can do this. Again, the reason we are bounding from above, and this factor is always less or equals than 1. And so that's exactly what we wanted to bound. This sum, this average, and now we bound it in terms of an times some power times some Legendre polynomial. And I think I made a mistake. You didn't catch me, but you see, I cannot, if I'm pulling out something from the sum, I cannot still sum over it, right? So this should have been L plus 1. And again, here, something that I'm using, which is another property of Legendre polynomials, that if the argument is larger than 1, that's a monotonic function of spin. So again, I'm taking the smallest spin when it's minimal, and since I'm bounding from above, I can majorize it with this thing. Okay, now it's legit. So now I have some L plus 1, S, N plus 1, and this is what we wanted to bound. So now there is still some just little technical steps. I don't want to spend too much time over it, but the basic idea is that now we write that high spin is less than this Legendre. Let me write it in the denominator here. And this guy we can move here. Prime. Okay, so now effectively what we will do, we will just take this bound and we'll plug it into the formula for the total cross section, because we say we bounded low spins, and now we said that the high spins are bounded by AN. Again, you didn't. This should not be as prime, it's already S to the n plus 1, here Legendre, which depends on the splitting spin. Okay. So then there is a little still algebra you can do with these Legendre polynomials. There is again still some property where you can bound Legendre polynomial from above, which again a property of Legendre polynomials. You can see check them in the notes. But the punchline of this analysis is that so I'm plus, okay, let me write it plus formula 97 in the notes. You don't want to write it, spend time on it. Which is again a fact about Legendre polynomials. We get the following formula. So the average cross section is less or equal, and here you see we have here L plus 1, L plus 2, and L is something that I will be choosing, and let me tell you that let's say that L is large. And we will check later that indeed will be large consistently, so then I can draw this plus 1 plus 2. So we get 16 pi L squared. This is low spin. And the high spin gives 16 pi squared an s to the n phi naught. Phi naught is just a number between 0 and pi. It's something which comes in this algebra with Legendre polynomials. So just believe me that it's a constant up to you. And here you have 1 plus 4m square root cos phi naught to the minus L. So this whole business, which might be a little bit mysterious, it's simply bounding this Legendre polynomial. It's just a fact of life that you can bound Legendre polynomials like that. So now you see what happens. That low spins contribute like a power, and high spins are exponentially suppressed. And so this exponential suppression is really something that we learned from this analyticity. And okay, now we have step 3, which is extremize with respect. So this is a true bound, which is true for any L. So let's just extremize with respect to L. And we get that, you can check that, it's an exercise. The extremal spin is this. At large S, so we are interested in large energy. And so again, so I told you that let's assume that L is large, and you did this, you see that it's large, so it was a self-consistent assumption. So this is extremized by this guy, and we get, if we just plug it into this formula, we get that sigma total averaged over S is less than or equal than 16 IS 10 minus 1 log S naught over 4m cos phi naught squared. So that's it. That's cross-R bound. It still has, remember, compared to the last time, we just get this. We just got log squared. This is related to the fact that we are averaging. So the averaging gives this extra power of S. So if we differentiate, we get back, we'll get back this log square. So there are still few wrinkles. So there is this N, there is this phi naught, and then in fact, if you use this result, and you again work a little bit, you can show that you can set phi naught to 0. That's an optimal. Okay, well that's an optimal bound. We set phi naught to 0, and we said you can set n equals to 2 with some extra work. So and then if I also work, let me say n equals 2, phi naught equals to 0. And then if I, you just get plugging here, that this sigma top is less or equal pi over m squared s log s squared. And in fact, there is still some little wrinkles. There is this s naught. There is this thing, this is asymptotic. In fact, you can write a completely legitimate formula, which does not have any of this. This is what we discussed yesterday in the evening. And this formula is in the notes. After formula 102, you will find, you can, if you're interested, you can look up and find a more precise formula. But this is, so this is the final result, and I hope now you have an idea how to derive a cross-R bound. Any questions?
Emanuele Coppello asks if it's not clear to me how you chose the value of L star.
Yes, so L star is up to you. So what I did is that I just extremized with respect to L. So differentiate this with respect to L and set to 0 the derivative. And I say that this is an optimal bound. That was done, yeah. But intuitively, it's kind of, yeah. It kind of makes sense if you play with it a little bit. Any other questions?
Okay, this M is really the M pi of last time. It's where the cut starts, so it's the exchange particles mass. It's not the external particles mass.
Okay, yes, very good. This M here, if you go back to the derivation, that's a good point. That's an important point, yes. Thank you again for the question. So this M here, the question is it related to the mass of the particle? Is it related to the gap? Or what it is related to? The answer is that it is related to the region of analyticity. So remember, we start with this AN defined as an integral. Here was imaginary part T, S, and we put some R. So this R that enters here will enter here.
Right, but I mean, the reason why I'm asking is that in yesterday's argument, this was the decay of the Yukawa, yes. So it has to be the
very good. We will discuss hopefully later today that this is related to that. Yeah. So questions? Any more questions? Shall we take a break?
Yeah. Before the break, yes, just a small announcement that tomorrow the lectures of
Simone and Sasha.
the section of Simone and Sasha will be inverted. So this means Sasha will be teaching in the afternoon and Simone in the morning. Good. Okay, let's meet again in
5 minutes?
5 minutes. Good.
Let's do that.
Russian against teaching.
5 minutes.
For the Italians in the audience would be 15.
Recording stopped.
Oh, thank you. That means it recorded what you were saying.
Yeah, but I already yesterday I started by saying
illegal.
It's illegal. So
I heard that. See.
And I was hoping to go to Florence for the lecture. I did them in Saclay like months ago.
Yeah.
So just doing the replay thing. It's interesting, and I was presenting this. Well, Slava was there all the time, and he was like, after I wrote the formula for AN. Okay, well, why we're doing that? That's obvious. So just show us how Markov extended the analyticity domain. Show us the proof of the extension of the analyticity domain, which is the core of this thing. Right.
Yeah, it sounds well. Okay. I mean, it's true that these manipulations are not.
Yeah, if you haven't seen them, I think it's useful to.
Yeah, it's useful to see, but I can see why you would say, okay, it's not. You're
of
bounding
course,
stuff, so you
of
start
course.
extracting things.
No, yeah.
But of course, I wouldn't come up with that problem, but I can understand why somebody could say, okay, this is not the core. But I was a bit surprised by what the comment on the temperness of the T product, because it seems like I mean, it's not a very hidden window. I mean, it's not. This thing I remember, like in the review by Martin. This sick review on
By Sommer or?
Sommer, yes.
Yeah.
I mean, they discussed this first part with LSD, with this version of the commutator rather than the usual T product, but okay, there are theta functions, and I don't remember, but I thought they were pretty careful with what.
Well, Slava told me, Ellipse temperedness of this T product. Apparently, I don't know.
Because you have a theta, you're multiplying two distributions.
Yeah,
so you
yeah,
have theta
yeah,
times
yeah,
one
yeah,
function.
yeah,
So, okay, but I mean, it seems like to the level of for the level of detail they go in this Dyson, Freeman Dyson, whatever theorem, all this stuff.
Yeah.
Like leaving aside something this big, like you cannot multiply two distributions, seems strange. It seems strange that there is no way out for the things they were doing. In the
Yeah,
details.
apparently Slava told me that in all papers like Lazar, this is kind of done. So
Yeah, it's a bit like it's a rather obvious problem, but since it's too hard to solve, we just
exactly. Yeah, it's one of those. Or maybe now Slava got interested in it.
So yeah, I mean, my question is just if we do this as a function.
I don't understand actually. You can't put two distributions.
Distributions bad things. You don't get a distribution when you multiply. Yes, exactly. And even delta square is like obvious. It's not theta anymore, but even delta times theta can give you troubles if the arguments coincide at some point.
Basically, yeah, you give it to
Just something like this. Yeah, so it's
at the bound
you can run into
where
troubles.
the bounds are satisfied, you have
Because sigma is a distribution. That's why I was confused.
I mean, it's a boundary. I guess. Well, probably Sasha, you can answer that question. Well, why is sigma distribution rather than that?
So well, it's rather just it's from the start we consider this Hilbert space, and so this matrix is a function of the Hilbert space and the space of L2, and here we sit at the point. So it's not something. It's not. It's not normalizable with functions. I mean, it's true also that we never do the experiment. We do the experiment with energy, it's always an average.
Yes.
It makes sense that it's true that we never average a central cross-section.
I've never seen
Always have some beams.
Infinite.
Yeah, it's just you do not expect to have some features there, but I guess if we have some very tiny feature, we just not see it.
It's not really the king, but okay, so it's yeah, because the fact that this is the cross-section, which is a plastic part, equal 4 should turn them on. Equal 4 and whether the results you can compute are falling in this method. Since your laptop always falls to the ground, give it a laugh.
No, I'm ready. I see the surface. This surface, I'm not worried.
From concrete to steel.
Yeah. I already seen it falling on all surfaces, and so nothing will happen. There will be trouble.
I see. So if I break it, probably my insurance. I will use the same.
You can't. Gotcha.
It might just diverge.
Yeah.
I guess 5 minutes have passed. I'm present.
Everyone has an iPad, by the way. Is that it?
I have this because Joao bought it. You should ask Francisco for that. Maybe. Asking the wife for an iPad.
That was yeah, everyone's got one.
Bene,
Uno, no, perché lo
questa è
scherzo.
una scatola che non ho mai non lo uso ancora adesso.
Ok.
Recording in progress.
Let's continue. So the next thing I would like to talk about, so this was the first part about what was about axiomatic analyticity and derivation of the cross-R bound. This is supposed to be as rigorous as it gets in this subject. Now I wanted to talk about something less, maybe less rigorous, but also more intuitive. Here's analyticity from unitarity. Let me remind you what was unitarity condition that we discussed. So we consider discontinuity in S, T, S, and T, which was equal, defined as the going above the cup, going below the cup, divided by I. This was equal to the sum over n particle states and the integral over the phase space, if you remember, of n particle states. And here we have t to 2 to the n, dagger. So the first thing we can immediately see from this equation is that let me draw a picture which will express this equation. And this picture will be just a graph, and it will look like a Feynman graph. So I will start slowly now building this connection, but it's not a Feynman graph. It's just a graph where all the particles are on shell at this point. So what do I have? Well, we have two particles, and then let's say I have n particles here, so this term, and then I have a disk. So if I have this graph where two particles go to n particles and go to two particles, I can associate to it naturally a term in this equation where this red line means a discontinuity, and the fact that we have n particles means that we have n lines. All these particles are on shell, and we do the integral here. Now, as we discussed, to produce n particles, you need energy, which is m times m squared. And so, since we have a discontinuity, we can associate to this graph a branch point in S plane, which starts at S equal n times m squared. So this is the simplest possible connection between unitarity and analyticity. And this kind of things, these branch points, are known as normal thresholds. So at this point, you can ask, is it possible that the only thing that we have is just a bunch of normal thresholds? So in fact, we are looking at the functions of t, s, and t. They're completely analytic. They just have normal thresholds in all channels, and that's it. So you can ask this question. And the answer to this question is no. So let's try to see that. And the way to see that is the following. You can, we were just discussing in the first part of the lecture that let's say we choose some s such that we have some term here. For example, we can choose on the simplest term n equals 2. So s is between, say, 4m squared and 3m squared. And we were discussing that this functions, everything that is written in this equation is an analytic function of t. There was analyticity in a lemon ellipse. It was a Martin's extension. What happens if we try to analytically continue this in t and we just assume that there is nothing but normal thresholds? So according to our simplest hypothesis, there are just normal thresholds. Let's see what happens to normal thresholds if we plug them to unitarity. So to do this, what you have to do is that, of course, this unitarity equation was written in, let's say, S channel. Let me remind you, S channel was S larger than 4n squared, t negative. But in fact, everything that is written here, you can do it very explicitly, is analytic function of t. Even that you can rewrite the phase space integral and see that everything is analytic in t. So you can just take this equation and analytically continue it in t. And if you just start with an assumption that you have simply just 2 to 2 scattering, so let's say just normal threshold, you find that this integral develops a new singularity. This new singularity is easy to understand, and let me again draw a graph, which is similar to that. What happens is that each of these guys will develop a normal threshold in the T channel. So this is a normal threshold in the S channel. But of course, it has also its identical particle. It also has a normal threshold in the T channel. So as you analytically continue in T, you will find that this integral, because of the normal threshold, develops an extra non-analyticity. Let me draw a picture for that. So let me start with this picture. So I have a term as n equals 2. Where each of these blocks is the amplitude itself, t2 to 2, t2 to 2. And as you analytically continue, what happens, each of this amplitude develops a cut. This normal threshold in the T channel, and well, what happens on this cut is that you have, again, the similar formula like this, but in the T channel, and you can draw a picture to this, which is like this. So what you find is that, in fact, just from the fact that the amplitude has normal thresholds, both in S and T channel, and from unitarity, you find that the right-hand side develops an extra discontinuity, non-analyticity in T, and so this corresponds to the double discontinuity of the amplitude. So analyticity plus unitarity plus normal thresholds lead to double discontinuity of the amplitude. Now, again, on this graph, what exactly is the meaning of this graph? At the moment, it's not completely clear what's the meaning of this graph, but I want you to think about this graph corresponds to the operation with the unitarity equation. So first part, reading it from this, means that we took the amplitude and we wrote a unitarity term with n equals 2. And what this means here below that, we actually continued in T and we got into some singularity where in each of these terms, 2 particles went on shell. So these graphs are graphs which are, all the particles are on shell. In fact, you can check that if you do these operations, there is a momentum conservation in every vertex. And this picture corresponds to a certain non-analyticity. And after this picture corresponds to normal threshold, and this is where the amplitude develops a singularity, discontinuity. These type of pictures correspond to Landau curves. Landau curves. And this is where the amplitude develops double discontinuity. So you can take discon T and discon S. Now you can be very, if you think very naively, like this diagrams looks like Feynman graphs, right? So these diagrams look like Feynman graphs. The only difference, and the crucial difference, is that here in every vertex stands a full non-perturbative amplitude. And in Feynman graph, instead of this non-perturbative amplitude, we really just put phi to the 4 vertex. That's the difference between these graphs and the Feynman graphs. And of course, here also all the particles are on shell. And in Feynman graphs, this is a loop momenta, we integrate over the loop momenta. However, there is a relationship between the two. And in fact, if you study the analytic structure of the Feynman graph, you will find that the functional difference, the functional dependence is different. However, the position of branch points will be the same. For example, if you take this graph and if you compute this bubble, which is a Feynman graph, just take this diagram and phi to the 4, you get some function. The precise form of the function is a perturbative notion, but the fact that the cut starts at 4n squared is non-perturbative. It's a completely non-perturbative fact. Similarly, and if you take this graph, take it like this, just put here phi to the 4, you compute this function. Its form is, of course, perturbative and has nothing to do with non-perturbative physics. But its analytic structure, it simply encodes unitarity, because that's what Feynman graphs do for life. They solve unitarity perturbatively. If you look at the double discontinuity of the Feynman graph, you will recover that again, it has a support along the same Landau curve. And so I haven't explained it, sorry. Normal thresholds is a statement that this discontinuity starts at s larger than, say, n squared. And Landau curves, these are the curves along which the double discontinuity of the amplitude. This is usually called rho. This was introduced by Mandelstam. So d disk of the amplitude, which is equal to discontinuity in T, discontinuity in S. So it's the same as what's written here. Just do it twice, once in S, once in T. This is proportional, it has support along some theta, and you have, say, for example, T is minus some TL of S. And this TL of S is the shape of the Landau curve. It's where the double discontinuity develops a non-trivial support, like a discontinuity develops along normal threshold. And for this graph, these are algebraic curves, by which I mean they're given by polynomial equations. And for example, for this graph, the Landau curve is given by the following equation. S minus 4n squared, T minus 16n squared, minus 64 10 to the 4. And so at this point, you can derive this equation, for example, the way I explained it, in two ways. First, you can take this unitarity equation, write it for n equals 2, assume that this amplitude has a normal threshold on the T channel, analytically continue in T, and you will see a pinch along this curve. This is the first thing I told you. Second thing I told you is you compute this Feynman graph in phi to the 4th, and you literally get the function, you take a double discontinuity. you will find that it's again developed like along this curve. Now, of course, the second thing sounds like an overkill. Because we don't care about the functions, we only care about the position of singularity. This seems computing like an overkill. And indeed, there is a third way. And the third way of establishing the analytic structure of the Feynman graph is solving Landau equations. Question?
Yeah. So just to see if I'm following, the reason why this threshold is anomalous is because the particle that the place where this discontinuity starts is where the incoming particles have enough momentum, which is not the same as the external particles. Is that true? So there is an internal line; it can exchange a different momentum than the original T. So, because I'm guessing like this bubble, the T bubble you have will start when the two incoming particles have a normal momentum.
Yeah, that's
produce the two particles, but the one horizontal doesn't have to have the T, doesn't have to contribute with the same T as the external one. Is this correct? Or not?
This is, I don't think this is correct.
Okay.
So it's, yeah, so I think you're emphasizing a very good point. You would think, you could have naively thought that, well, we go to S larger than 4, we get a threshold, S equals 4. We go now T larger than 4. Why don't we get just a threshold T equals 4? And the truth is that we don't. Now, it comes out from unitarity equations, it comes out from the Landau equations. It's hard for me to think intuitively in terms of what you said, because something which worth emphasizing is that the support of this curve is when S and T are both positive. This is not a physical region. So these particles, even though they're on shell, their energies can be complex. And this is why we will analytically continue. We will analytically continue in T. So this is in fact some non-trivial curve. But what I want to emphasize here, I hope I'm now slowly getting into that if you care about non-perturbative analytic structure of scattering amplitudes, as is it constrained by unitarity, you can study Feynman graphs. Because Feynman graphs, they have the same unitarity type structure if you look at their cuts. But you do not care about the form of Feynman graphs, you care about singularity of Feynman graphs, because effectively, what going from perturbative to non-perturbative is taking this vertex and shrinking it to a point, but this vertex being a full non-perturbative amplitude of phi to the 4 will not affect the position of this singularity. This maybe requires some thinking, but I think that's the true fact.
This is because these diagrams and Feynman diagrams are just a bookkeeping device for the kinematics.
Exactly. That's a very important point, that all these curves, they only know about the masses of the on-shell particles and phase space integrals. There is no dynamical assumptions about perturbation. To get these curves, it's only fixed in terms of the kinematics. However, instead of studying these phase space integrals, it's easier to study Feynman graphs. And that's why people in the 60s, there was a whole school which says, okay, we want to understand non-perturbative analytic structure of the amplitudes, but we will study Feynman graphs. Just want to emphasize that Feynman graphs is a tool to study non-perturbative analytic structure.
Sorry. I just want to know if I'm understanding correctly. The formula you wrote under the graph is gives you the Landau curve, right?
Yes.
Okay.
Yeah. So this is a philosophical point to have in mind. And so after you see that it's useful to study Landau, study Feynman graphs, then then you can just go ahead and study Feynman graphs and their analytic structure, and that's what people did. And in fact, what they did is that study Landau equations. Landau equations, and these are equations which you apply. I guess you mathematically write this. Feynman graph. So what are these equations? Well, these equations I already motivated them. You just take a Feynman graph, let's say this one, and then you associate, you put all propagators on shell. Then energy momentum is conserved at every vertex. And finally, something which is not less intuitive is that you associate to every leg some parameter alpha. And along every loop, this alpha I, ki has to be 0. Now, in the simplest situations, this alpha has to be positive. Let me just say that this alpha has to be positive. What is the meaning of this? You can think of this alpha as a proper time. And what does Landau equation says? Landau equations is the conditions for which they're necessary, the necessary conditions for the singularity, development of singularity of a Feynman graph. These are conditions for which you can look at the Feynman graph as a movie in a classical spacetime. If you see a movie in a classical spacetime, what do I mean? You have particles which propagate on shell, so they're really on the classical trajectories. They bump into each other, these guys propagate on shell. But to make a movie out of this in space-time, if I have a loop, something happened here, something happened here, something happened here, something happened here, it should sum up to 0. If I start at a certain point and I want to associate to some process in space-time, then it should sum up to 0. And this alpha I has a meaning of a proper time along the line. So you think of this condition that we should be able to associate classical space-time movies to the Feynman graphs. And so what you find is that given a certain kinematics, given S and T, you cannot always do that. But if S and T are on this curve, you can do that. And there is a famous result by Coleman and Norton, which says that all singularities in the physical region of any amplitude, so M to M, correspond to the movies, the Landau movies. So, and here the important point, physical region is really something you measure in the experiment. For example, S and T going both positive, this is not physical region. So this is a comment aside. Just, it's a famous result about singularities of the Feynman graphs in the physical region. So they show that the necessary condition for the development of the singularity is that you can draw a classical movie. But in any case, at this point, it's clear that these conditions do not care what you put in the vertex. So you put derivative, you don't put a derivative. This is really something on shell, and therefore it has a chance to be non-perturbative. So now I want to, at this point, I motivated the connection between Feynman graphs and Landau equations. And in fact, it's an interesting subject to study these Feynman graphs and their singularities. But I would like now next to discuss a couple of examples, which are sort of the basic two canonical examples, which you should keep in mind when thinking about the singularities of the amplitude. So any questions about that? So for this point, at this point, we will encounter the explicit solution of this Landau equations shortly, but at this point, I just want to tell you that we started by asking about analytic structure of the amplitude from unitarity equations. We saw that the naturally developed pinches, normal thresholds, and this sometimes called anomalous thresholds, but I don't. There are various terminology. Let me call them Landau curves. So there are more complicated analytic structure which are Landau curves, and exactly the same singularities appear in Feynman graphs, and their position is controlled by the Landau equations. So that's what I explained so far. Now, how do you mathematically derive these equations? They do not come from some complicated thing. They just come from the fact that if you have an integral, and think of the Feynman integral as an integral in you integrate over some loop momentum, right? With some I epsilon prescription, so it's you can deform this contour. When does the integral over the complex, say, loop momentum develop a singularity? Well, it can develop a singularity in different ways, but the simplest one is that if you have a pinch. Because if you just have one pole, let's say you have a pole that comes to the integral, well, then you can just deform the integral, you do not have a singularity. But if you have two poles from the singularities, then you cannot deform the contour, you have two poles and you have a singularity. So Landau equations are just by definitions simply the conditions for the pinches of the integrations of the Feynman graph. So there are various ways to derive it. I think there are some in the notes, but literally it's the same as you do the integral over dz. You do the integral over dz 1 over z minus a, z minus b, and you think a little bit how this integral can develop a singularity. And you will see that this integral can develop singularity in two ways. One is that when this pole approaches the end point, and the second when a and b pinch the contour. Question? No? Okay, now I want to discuss two canonical examples which I think are very useful, which illustrate some of the things, and I will now talk about Feynman graphs. But I will only care about their singularities because this is a non-perturbative thing. So first graph which I would like to discuss is something which people call anomalous thresholds. And for some reason, maybe because of a name, this is a topic which has some reputation of being fearful, scary, mysterious, but it is in fact something very simple. And this anomalous threshold, and anomalous at this point will be something that it will not be a normal threshold, it will be something else, is related to the following question. Imagine you have a, say, electron, or let's say you have even photon, and you want to probe some object electromagnetically. So how do you see something? Well, you see something by exchanging a photon with this object, and imagine that your object is composite. So then you can imagine the following situation. Let's say you have a probe, some I, which emits a photon, and then the photon interacts with an object like this. You have a particle, say, of mass m, and here you have a particle of little m. For example, you can imagine that this is some bound state positronium, which it's neutral by itself, so you cannot scatter a photon on it. But you have E plus and E minus, and then, in fact, what you will measure indeed that you do couple to this object, but you couple through this one of these constituents. This is a process have in mind. This is just a Feynman graph. Here I'm drawing a Feynman graph. And let's say there is a momentum flying here, which is q. And the question I would like to ask is, what is if you see this object m through this diagram, what is the size of this object? Well, the simplest, for example, if you have a point-like particle, like electron, that's it. That's a diagram. It's a, it's just a constant. If you do Fourier transform, you get a delta function, and this delta function is a statement that the object is point-like. What is the size of this object? This is a question we are asking. Now, how do we ask this question? Well, we ask this question by computing what's known as the electromagnetic form factor, which is just this. You take, say, particle with some momentum p, you transfer to it some momentum q, and it has p plus q. And here you have electromagnetic current, and in my lectures, everything is a scalar. Nothing carries Lorentz indices, so for simplicity, I just consider every particle here being a scalar particle. Now, how do we compute the size of the object starting from this? Well, we just do the Fourier transform. So we take f of, say, so value x is equal to the Fourier transform of this form factor. So that's what it is. Now, this Fourier integral is a very useful, is a very important thing, because it appears in so many contexts in the S matrix theory. Whenever you're switching from momentum space to thinking about momenta to some impact parameter space, always do this integral. An important thing about this integral is the following fact, that if you take, now I'm asking, what is the behavior of this Fourier transform? At large, let me call it R, some distance R, at large R. Well, for point like electron, we already discussed it, it's just a delta function. But let me consider, for simplicity first, before computing this Feynman graph for you. Imagine that we are doing Fourier transform of something like this. Plus m squared. This is just a math exercise, and this is how you get your cover potential. You will find that under Fourier transform, it will give you something which decays like this, mr. And the point here is that you see that this integrand is non-analytic at Im. So it has a non-analyticity at Im. And in this particular example, the closest analyticity in the complex plane is controlling the size of the object. In fact, this is completely general. And the idea is that you evaluate this integral. If you want to take large R, you evaluate this integral by deforming the contour in the complex plane. And then you hit the first singularity, say here Im, and then effectively you just evaluate it on the exponent, and that's what you get. So there is this connection between the nearest non-analyticity and the size of the object, if we define it like that. So at this point, what is clear to us then, what we need to understand is the analytic structure of this diagram as a function of Q. And the size of the object will be the position of the leading singularity. For example, if this diagram has a normal threshold, which is just minus, so Q squared, I define it as minus Q squared equal to 4 little m squared. If this is the diagram, say For example, this would be the situation for the bubble. If the diagram is like this, then we will have a Yukawa potential with of this type. This is a second, little bit more complicated example. And finally, let's evaluate the triangle. The triangle, just I'm just telling you the answer. You can introduce Feynman parameters for this graph, and you have delta 1 minus some of alpha I, and here you have n squared minus alpha 1 plus alpha 2, alpha 3. N squared minus alpha 1 alpha 2 q squared. This is just a QFT textbook evaluation of the one-loop graph. And in fact, there is a very simple formula that is written in the notes. If you take the derivative of this function with respect to little m squared, there is a simple formula that is written, it's formula 115. Just a bit bulky, I will not write it. It's something like log minus log, some arguments, and here you have m squared, q squared, minus 4 capital M squared plus m to the first. So it looks like something interesting happening. Because if you look at the singularity of the denominator, it is located at the following locus. It's located where this thing is 0, which is q squared minus equal to 4m squared minus m squared minus 2m squared squared divided by m squared. However, we should also check that on this pole there is no cancellation between the logs. And this is an exercise, but you can check that this is indeed a branch point of the integral whenever, strangely, m squared is larger or equal than 2m squared. Note that this 2 is not under the square, it's just 2 times m squared. So this branch point of this graph is called anomalous threshold. You see it's anomalous because it's not a normal threshold will be q squared equal to 4m squared. Here we have something which depends on this other mass, and so it looks more complicated. Now, could we have expected this thing to be here from the start? And the answer is yes. How could we expect this thing to be there? Well, let's imagine that we scatter positronium. So the positronium has a mass m equals to 2m plus some binding energy, which can be computed in quantum mechanics. So it's a loose bound states of electron and positron. So because it's a bound state, this En Es is negative. Now, what is the size of the positronium? Well, size of the positronium, you solve the Schrödinger equation, you get Bohr's radius. So let's plug this formula, m equals 2m plus e here. We will find that q squared is equal to 16m times Em bound state. And I told you that this is a non-analyticity. And the position of non-analyticity, which is responds to complex momenta, the position of non-analyticity defines the size of the object. In our example, the non-analyticity was at Im, and the size of the object was 1 over m. So here, the non-analyticity will be square root of this. So the size of this object is this. M. And you can check that this is Bohr's radius. So in fact, you get from this diagram that you see electromagnetically positronium as the size of the object the same as you expect it to be. However, more generally in some relativistic setting, if you have this triangle graph, the size of the object will be this. Well, the square root 1 over. Now, what is the lesson from that? Well, first of all, this also relates to Marcos' question. Remember, if let's say now we plug, this is related to the region of analyticity. So if we plug it to the Froissart bound, this will be the size of the object, which is again makes sense. And second, what's the lesson is the following. If we look back to this diagram, so if we look at this diagram in the S channel, which is from here, so that the energy is here, say some S, some Q square. Well, when is this process possible? Say, if these particles have some mass m, this is possible for S equal Q square equal 4m squared. This is just only when this physical process is possible. And if we write discontinuity of this object, for this S, for physical S, we will find what we found before. It just satisfies unitarity. However, when we go beyond the physical S, when we go, say, for S less than 4m squared, then you should not expect that things always just nothing happens. Here's an example where you go for S built for Q squared less than 4m squared, and there is in fact another branch point at this position. So you should, in some sense, when you go for S less than 4m squared, you should think of this diagram as seen from a different direction. So we put our I here instead, and what we really are thinking about is that it's a particle, and we're measuring its size. And this is controlled by the singularity for S less than 4m squared, and this anomalous threshold, it's really, you better think about it from a different channel. So this was one example. Maybe I should, because it's already time, I should stop here, and I will finish analyticity next time, and I will introduce dispersion relations. And now we stop. Maybe can I use 3 more minutes?
Sure.
Yeah. So let me just write it, and so.
We still have 10 minutes officially. No?
Well, we started 45 plus 45, then we bent it to 1 plus 1. So I'm just scared that students are already.
You made the 5 minutes break that you gave.
Yeah. So, okay, so the second example, which I just want to write one formula which connects to the first part of the lecture, which again due to Mandelstam, and the formula is the following.
Sorry, Sasha, can I ask something stupid about the previous? Why did you use for the size of the object is the definition of the form factor rather than say the total cross section, which is also the size of the object?
Yeah, you can.
So would you? I mean,
Well, I define size of the object literally. What do? We have an object. We have a probe. We exchange a photon, right? So that's how we literally measure the scene's size of something.
yeah.
of course, there is electromagnetic form factor, gravitational form factor, whatever. The way your eye works, then the size changes. So I want to consider the just the right one formula and finish with this thing is how actually Mandelstam introduced his representation. Mandelstam representation. And this is the story of a box graph. So consider just a Feynman diagram. And all particles for simplicity being equal mass. Already, if you take a Feynman graph where masses become completely generic, it becomes a horrible mess. A very complicated story. But the statement is that this is some integral of S and T. You can compute it, and it's equal to the following double integral. And rho has supported, it's a double discontinuity. You see, if you take one discontinuity, you kill this denominator, and now there's this one. It's supported along the Landau curve. So it's equal to theta prime minus 4m squared, t prime minus 4m squared, minus 4m to the fourth. This is a theta function, so it's only about these things. And here you have S prime t prime, 1/2. And here you have the same equations for the Landau curve. So this is a super nice representation for the box. And it has this Landau equations, and it has this analyticity domain, which is can be seen from here. You have a first discontinuity starting from 4, second discontinuity starting from this Landau curve, and Mandelstam introduced. Well, I think in the 60s everyone had this in mind, this connection between Feynman graphs and the non-perturbative unitarity, and so in fact he introduced this representation as a representation not just for the box, but for the non-perturbative scattering amplitude. So this representation was a double integral over this kernel, and we will discuss, maybe next time, I will discuss what goes into this Mandelstam representation, but this is a formula you should keep in mind for the Mandelstam representation. It hasn't been proven, but the simplest example that appears is this box. And here you already see some of the features: normal threshold, Landau curve. If you start changing the external masses, you will see that you develop anomalous thresholds. If you change them even more, you start developing complex singularities. So already just the story of a box is very, very complicated, but when all the masses are equal, it's just that. Let me stop here. Yeah.
Thank you.
Thank you.
Okay, are there any questions now, or we can prepare them for tonight?